Hello. There are some really common angles, and we need to be able to determine what the sine, cosine, and tan of those angles are because they are so common, and therefore they crop up in calculations all the time, not just in maths, but in sciences and stuff like that. And so knowing them off by heart is great, or at least being able to get them from a table so you don't have to reach for your calculator every single time. Here they are here. In a previous video, I demonstrated how this little section here, these acute values here, are the values of the acute angles listed up here are determined. It's really worth watching if you haven't already. I'm going to take it as given that you can see what you have to do here. Cosine of, and then pick an angle here, and then the result is this thing here. So for example, this is pi on 6, 30 degrees, 45 degrees, 60 degrees. So if I was trying to work out the cosine of 60 degrees, I'd go up here, here's pi on 3, 60 degrees, down to the cosine line, it's 1/2. Or the tan of 60 degrees, I'd go down to the tan line, it's √3. And this is the exact value. We call it exact because there's no approximation. We're not converting it into a decimal and rounding it off after 900 decimal places or 2 decimal places. It is exactly the square root of 3, or exactly a half, or exactly the √3 on 2. So these are a bunch of acute angles, and then these ones here, 0, pi on 2, pi, 3 pi on 2, and 2 pi are called boundary angles, and they're pretty common as well. And I'll explain why they're called boundary angles over here. Here I have our cast diagram as per usual. I've listed the quadrants as we normally do, quadrant 1, 2, 3, 4. And what I've got over here is the angle measurement of the unit line here that is made with this quadrant 1 x-axis. So if the line is flat against here, then that would be 0 degrees. There's no angle formed. Or I've gone all the way around and back to the start again, so it's 360 degrees, or 0 and 2 pi if you want the radian measure. Up here, it's 90 degrees, or pi on 2. Up here, it's 180 degrees, or pi, it's a straight angle. Here, it's a 3/4 angle, so it's 270 degrees, or 3 pi on 2. And as I said, we're back to 360 again. So what I'm going to do is I'm going to use that sort of first principles unit circle approach to determining what the sine and cosine and the tan of the boundary angles would be. I'll be as quick as I can. It's not too bad. Let's have a look at this one here. This one here, because the unit line is of length 1, it means that the x-coordinate must be 1, because it's gone across by 1. I'll use the same colour. And I haven't gone up at all, so it's 1, 0. But also we know the coordinates are cos of theta, and theta is 0 in this case, and the sine of theta, that's the usual xy coordinates, using theta instead of other coordinates. So we've got cos 0 and sine 0 as being 1, 0. Cos 0 is 1, sine 0 is 0. I encourage you to pause the video now and maybe try and fill in the other coordinates and therefore what the other cosine and sine values are without looking at that table of values. So pause the video, come back. I'm going to assume you have done the pause, and if you haven't, tough luck. What's this here? This orange line here has gone up 1 unit, but it hasn't gone across at all, so it's just 0, 1. And that means that the cos of 90 degrees, I'll use the radian measurement, the cos of pi on 2 is equal to 0, and the sine of pi on 2 is equal to 1. Alrighty, what about the green line? The green line has gone backwards, so the coordinates are -1 for the x-coordinate and 0 for the y-coordinate, which means that the cosine of pi, 180 degrees, is -1, and the sine of pi is equal to 0. Let's just do a quick check to see that that does confirm what's on the table. The cosine, where's pi? The cosine of pi is -1, because it's gone back. The sine of pi is 0. That makes sense. It all is working out nicely for us. Finally, the red line has gone down by 1, but certainly hasn't gone anywhere sideways. So we have the coordinates 0 and -1 for the y-coordinate, which means the cosine of 3 pi on 2, 270 degrees, is 0, and the sine of 3 pi on 2, 270 degrees, is -1. And that completes it all. And I won't write it in, but if we go back to the start again, we'll have the cosine of 2 pi and the sine of 2 pi being 1 and 0 respectively. So that's sine and cosine defined, and we just need to now worry about tan. Now tan is, if you remember from a couple of videos ago potentially, tan is simply the gradient of these straight lines. So we just need to consider each of the straight lines in turn and say, well, what would the gradient be? And that will be the tan of that angle. So what would the tan of 0 be? Well, the tan of 0 is this flat line here, and therefore it's got a gradient of 0, so the tan of 0 is 0. What about the orange line? In the orange line, the line is vertical, and you should know from your function study that a vertical line has an undefined gradient, because if gradient is rise over run, then the run in this case is 0, and you can't divide by 0. So we can say that the tan of 90 degrees, pi on 2, sorry, I keep on putting brackets in, which you can do, but I'm just trying to be consistent, is undefined, doesn't exist. For the green line, we have the same gradient as we did for the blue line. It's just a flat line. And so we can conclude that for tan of pi, the gradient is 0. And finally, for red, for the vertical, it's another vertical line, and therefore we have the similar situation of tan of 3 pi on 2 is also undefined. So it's undefined because there is no run, and therefore we can't figure it out in terms of a gradient. And that's, as you can see, clearly identified here where it says undefined. Okay, we're going to wrap up with just a few examples of how we can bring all this together, the exact values, the boundary angles, and how we can use our knowledge of the quadrants in order to solve problems beyond 90 degrees. So I've got sine of 5 pi on 2 as my first example. So we're going to follow the usual 3-step process. The first process is work out where the angle is going to land us. So I start, as always, at the quadrant 1 x-axis, and I start going in an anti-clockwise direction. Now, how do I work out 5 pi on 2? Well, I know that each corner here is going up by pi on 2, so I'm just going to count. 1 pi on 2, 2 pi on 2, 3 pi on 2, 4 pi on 2, 5 pi on 2. So we end up with this lovely kind of little spiral thing. That's 5 pi on 2, and I'm landing on the boundary. So I can state, this is a little bit like working out the reference angle, but not quite because it's a boundary angle. I simply state sine of 5 pi on 2 is the same as, that's what the equal sign means, is the same as the sine of pi on 2. And that is equal to 1, which you can use from your logic, 1 unit up, or from your table of values. Tan of negative pi is example 2. Same approach. Where is it going to land? Now the negative means we're going to go backwards, which means a clockwise direction. So I start from the x-axis of my quadrant 1, and I go back pi on 2, back to negative pi here. So negative pi will land there, which I'll now draw in, like so, but I've got an arrow to show that I've gone that way. So I've got negative pi there, and so I can conclude that that's going to be the same as the tan of the boundary angle pi. And the tan of pi is 0 because it's a flat line, and I'm done. Tan of negative pi is also 0. Example 3, sine of 120 degrees. Finally, something a bit more interesting. 120 degrees. So again, knowing your boundaries here is really important. We've got 0 to 90 here, and then 90 to 180 here. So 120 definitely exists in this section. You don't have to be accurate with this next bit. You just simply put a line in, like so, and then draw your angle in to show that you know that's the 120 degrees. And we know that the sine of 120 degrees is going to be the same as the sine of the base angle or the reference angle, which is the angle from the x-axis to the blue unit line. So that's not too bad a calculation. It's just going to be 60 degrees, isn't it? Because they both will have to add up to 180. That's not too bad. So we can say with a little gap, sine of 120 is the same as the sine of 60 degrees. I leave a little gap because I then need to confirm whether it's a plus or minus. Our cast diagram says cosine in this quadrant all in this quadrant, sine in this quadrant, and tan in this quadrant. So sine is positive in this quadrant, and so sine of 120 is the same as the sine of 60, and the sine of 60 is root 3 on 2, which you can eventually know off by heart, or you can go to your chart and say, 60 degrees, I know that's pi on 3, I'm looking for sine, so there's my value there, root 3 on 2. So that's that one done. One final one to do, which is example 4. Example 4 is the cosine of 5 pi on 4. So we need to work out, as usual, with our first step, where we are going to land. So what you need to get used to when dealing with radians is, in your head, figuring out how to change the boundary angles into the same denominator as what you've been given in the question, in this case, over 4. So, for example, this is pi on 2, which is the same as 2 pi on 4. So I've got 2 pi on 4, 4 pi on 4, which is pi, and 6 pi on 4. So I've got 5 pi on 4, which must be between these two boundary angles. And so I'm going to draw my blue line in here. And I'm going to do a pretty big angle and write 5 pi on 4 so that I've got room to write in here what this angle is here. So if it's 4 pi on 4 to get here, then it's another pi on 4 to get to 5 pi on 4. I don't think I'm going to fit it in. I think I'll just put it here. So that's that's pi on 4 is my base angle, or my reference angle. Okay, so what does that mean? It means that the cosine of 5 pi on 4 is the same as the cosine of pi on 4, and we need to work out the plus or minus of it. Cast diagram comes up. Cosine is positive here, all is positive here, sine is positive here, only tan is positive here, which means that this must be a negative cosine pi on 4. And again, we can use our knowledge or our table to determine that the final answer is root 2 on 2, or to be more precise, negative root 2 on 2, and you're done. Now it is your turn. Go to your textbook and go through the problems that are mentioned in the learning schedule.